Hello everyone, welcome back. This is the 4.A.2 lesson. We're going to talk about implications of the rate law. So we already had one about the rate law and how to derive the rate law and things like that. But this is specifically how we can apply the rate law to an equation. You'll notice I'm a little casual today. That's because it's a snow day. I didn't feel like getting dressed up just for some videos. I'm going to jump off the side and you guys can take down the notes and I'll come right back. Okie dokie. So, hopefully you guys had enough time to take down the notes. So this is our equation. It's a generic equation. Let me just kind of move some toys out of the way here. Alright, it is 3a plus 4b yields c plus 2d. Okay, so I just made it up, just tossed on some coefficients. And I'll give you the rate. So, you could, calculate the rate and all those other things that we've been doing, or find the rate law from a tabulated set of data and all that other stuff. But let's just say we have the rate. So the rate for appearance of C, so the rate specifically for C, is 25 molarity per second, or 25 moles per liter per second. So it is appearing at 25 molarity per second. Well, knowing nothing else, if we just look at our balanced equation, we know that for every 1 C, 2 D's form. So for every 1 C, there are 2 D's. Well, that means then that the rate of D is actually twice the rate of C, right? We know that. We know that for every 1 C, 2 D's form. Well, we can actually use that mathematically to our benefit. So we know that the rate of D would therefore have to be 50, right? Because if C is 25, and we know that for every 1 C there are 2 D's, well, D has to be 50. And the same is true for the disappearances of A and B. Now, we generally don't do rates of reactants, but we do know that since this C is forming at 25 molarity per second, we also know that A is disappearing at 3 times that rate and B is disappearing at 4 times that rate. Okay, so just thinking about the equation and tying our rates into the equation, that kind of gives us a lot of information. For example, let's say there was a question that was, how much did A disappear after, let's say 10 seconds. Okay, so let's say how much did A disappear after 10 seconds? Well, we don't have the rate of A. We don't even have a starting concentration or anything with A. But we know that C appeared at 25 molarity per second. So that means we know that C appeared over 10 seconds. C would have been 250 molarity, all right, or moles per liter. Now, obviously, it's a little clunky because we don't have the volume of the container. Otherwise, we would just kind of turn that into moles. But let's just work with me here. So after 10 seconds, we know that C is going to equal 250, right? But I know that A is 3 times of C. A equals 3C. Therefore, A equals 3 times 250, and I know that A equals 750 molarity per second. So, knowing nothing else than just the rate of A and having a balanced equation, I'm able to calculate quite a bit of information and even figure out how much my reactants are disappearing. Okay, so that's the video, nice and quick, not a very hard concept, but one that you can see is kind of pretty applicable and one that is kind of important. If we know the rate of one, using our balanced equation, we can figure out the rate of the others. It's really important that I stress right now, these are not the order of the reaction. So when we say the rate law and we raise it to the order, this does not mean that's a 3rd order and 4th order rate reaction. Not at all. It doesn't even mean that C is 1st order and D is 2nd order. It just means that D appears twice as quickly or twice as much. For all we know, C could be 0 order and D could be 1st order, or C could be 1st order and D could be 2nd order, or we could have a 2nd and 4th order. We could have whatever. It doesn't necessarily imply much about the equation, the rate law equation. It's more of a practical application. All right, hopefully that cleared some things up, and I will see you in class.